In this video, we will wrap up the discussion about free fall acceleration. So as we mentioned that free fall is the motion of an object in the absence of all other forces but the force of gravitational pull of Earth. We will ignore air resistance. We said it's a one-dimensional. And, objects move on a straight line. They can either be thrown up or they can be falling down. And because all these things mean that we can apply the equations of kinematics that we learned previously. When objects are under free fall motion, the acceleration is always downwards, so a negative sign, and the value is 9.8 meters per second squared. That value sometimes can be written as g. So we can say g is 9.8 meters per second squared. So in that case, the equations that we had previously for 1D motion on a straight line with constant acceleration, let me remind you what those equations were. So we had final velocity is initial velocity plus acceleration times time. Delta x is initial velocity times time plus 1/2 acceleration times time square. Final velocity square, initial velocity square is 2 times a times delta x. And delta x is 1/2 initial plus final times time. So these were done previously, and that was 1D motion with constant acceleration. Because free fall is nothing but 1D motion with constant acceleration, we can use these equations. It's usually helpful if we kind of rewrite these equations. So I will leave it like this. V is V0. So I'm going to make the following substitutions. Wherever I see delta x, I'm going to replace it with delta y. And wherever I see a, I'll replace it with negative g. So I'll get negative gt. You don't have to do that. You can leave a. Don't put negative g, but when put the value in, put negative 9.8. Either way, it is fine for me. Gt square, final square minus initial square is negative 2g delta y. Delta y is 1/2 initial plus final times time. So these are the equations of free fall motion. In that, you will remember that g is positive 9.8 meters per second square because I have already taken into account the negative sign. So please do not put another negative sign, otherwise you will end up with incorrect answers. Delta y is displacement along y-axis. Or vertical axis. The rest of the quantities have the same meaning: initial velocity, final velocity, time. So all those you're already familiar with. Anytime objects are going upwards, delta y will be positive. Anytime objects are dropped down, delta y is negative. So please remember that when you apply the equations. So as you know that for free fall equations, ignoring, that is very important, ignore air resistance. A is negative g. On Earth, again, I use G is 9.80 meters per second squared. It does not depend on, the value of G does not depend on mass of the object, density of the object, or shape of the object. If you drop a hammer and a feather um, from certain height, they will accelerate at the same rate of 9.8 meters per second squared. It does vary, the value of G, which is 9.8 meters per second squared. It changes with latitude, and elevations. So for example, the value here in Utica could be 9.83, I think it is something, but value in Death Valley, which is below sea level, might be lower. I don't know exactly what the value is. So as far as problem solving strategy goes, we have to follow the same method that we did for 1D kinematics previously. You will read the problem carefully, outline everything that is given to you, make sure you understand what is missing, and then come back to this set of equations right here, and you will pick one equation, plug the values in. If one is not enough, use one more, whatever you want. Our claim is that as long as you have enough information, you should be able to use either one of these and you should be able to get your answers. So I'm going to start with this example right here. It says if you toss a ball straight up, what is the sign of ball's displacement for the ascending part from the release point to the highest point? So you're starting from here, start, and this is the end point, and it is being thrown up. So what will be the sign of displacement as it is going up? So in this case, for part A, displacement is positive. Why? Because remember, displacement is final position minus initial position. The final position is higher, initial position is lower, so the answer will be positive. What is it for the descent part from the highest back to the lowest? So now if you start off here and go here and drop something down, delta y is negative. Part C says, what is the ball's acceleration at its highest point? No matter where the ball is throughout the trip, going up or coming back down, acceleration is always negative 9.80 meters per second squared. It remains constant. Just wanted to go over that quickly. In this example, let's look at that. Raindrops fall 1,700 meters from a cloud. So cloud is up there, right? Here is a cloud. And raindrops are going to fall from here and come to the ground. This is ground, and that's the cloud. Part A says if they were not slowed by air resistance, so ignore air resistance, how fast would the drops be moving when they struck the ground? So just before they strike the ground, what is their velocity? Let me make a list of everything that is given to us. So given information, we are given the distance that is traveled by the clouds, which is right here, but because, not by clouds, I'm sorry, by raindrops. But because raindrops are starting at a higher position and going to lower, remember in the previous exercise, we said delta y is negative. So in this case, delta y is negative 1,700 meters. Now, because raindrops are going to start from rest, nobody's giving them any initial velocity. They're not being pushed down from the cloud, they just fall naturally. So initial velocity is 0 meters per second. Other than that, that's pretty much it. What are they asking us to calculate? The final velocity at the end of 1,700 meter trip. So what is that? So that's the given information. Now we have a couple of different choices. We can, let's say, so for calculating final velocity, I can either use the first equation, but time is not given. So I'll have to have time calculated some other way. Or we can use the third equation that does not require time. So I think I'm going to go with the third one. V final minus, so V final square minus V initial square is -2 times G times delta Y. So final square is unknown. This one goes to 0, so I'll just remove that. -2 times 9.80 times -1700. So V is equal to square root of the negative times negative becomes positive 2 times 9.80 times 1700. So V comes out to be 182.54 meters per second. Now looking at the significant digits, assuming 1700 does not have an implied decimal, I can only keep 2 sig figs. So the answer will be 180 meters per second. That is a really, really fast speed. The question B says, would it be safe to walk outside during a rainstorm? Something hits you in the head going at a speed of 180 meters per second. That is very fast. But luckily, the mass of a raindrop is extremely small. So the impact is going to be minimal. You won't get hurt. Okay. This is similar to one of your homework problems, but a slightly different way of stating it. So in this case, a rock is dropped from a 100-meter high cliff. So cliff is up here, cliff, and the ground is here. And a rock is dropped. Let's write down the given data right away. Delta y is negative. Well, the total is negative 100 meters. But the question, let me wait until I read the question. How long does it take to fall the first 50 meters? So I'm going to use delta y to be negative 50 meters. So I'm only concerned about the first 50 meters. Okay, not the other 50 meters. So that's our delta y. The rock is dropped, doesn't talk about initial velocity. So initial velocity is 0 meters per second. And the question is saying how long? How long means calculate time. Time is unknown. So only initial velocity is given. We have no information what the final velocity is. And delta y is given. And we are asked to calculate time. So looking at the equations, I think number 2 will work better in this case. Okay, so let's box that. Delta y, v initial t minus 1/2 gt square, negative 50, 0 times anything is 0, 9.8 t squared. The negative 50 is negative 4.9 t squared. So get rid of the negative sign because it appears on both sides of the equation. E squared is equal to 50 divided by 4.9. From there, t comes out to be 3.1944 seconds, or rounded to, let me look at 50 as one significant digit, so that would be 3 seconds. Part B of the question says the second 50 meters. So now for first 50 meters, the object took 3 seconds rounded, but for the second 50 meters, the second part of the trip, how long does it take? You cannot say it also takes 3 seconds because the object is accelerating. So the speed is going to be different. So there are a couple of different ways of doing. I will do one way. You can attempt anything else that comes to mind. What I like to do is I will calculate the total trip time starting from the top to bottom, and then subtract the time for the first 100, sorry, for first 50 meters, and that will give me the time for the rest of the 50 meters. So for the total trip, delta y is v initial t minus 1/2 gt squared. Delta y for the total trip is 100. This term is 0 because 0 times anything is 0. And then I have 9.8 times t squared. So once again, t square is equal to 200 over 9.8. So that gives us a total of 4.5175 seconds. Remember, there's a square root also. The total trip time is 4.5175 seconds. Out of that, 3.1944 seconds were spent covering the first one half of the trip. So for the rest of the trip, the time will be equal to 4.5175, this is one, minus 3.1944. So the answer to part B is 1.323 seconds. Now round it to one significant digit, that will be 1 second. If you don't want to follow that method, you can try to calculate what would the velocity be at this halfway mark, and then use that and a different equation to find the time for the second 50-meter half. So as I said, there are different ways of doing this. But that kind of takes care of free fall. At the very end, I just want to quickly mention a few things where how do you use integration in motion analysis? Look at the graph here. Here they're plotting acceleration versus time. How do you get velocity out of that? Remember, acceleration was defined as derivative of velocity with respect to time. So that tells me that velocity has to be integral of acceleration over time. So, or in terms of graphical analysis, we will say velocity is area under acceleration time graph. How do you calculate velocity from here? So they're saying there are two time intervals, t0 and t1. The velocity between that, how does do you calculate velocity? That will be delta v, which is v1, v final, and v0, and that is going from initial time to final time, ADT. Okay. This will rarely happen. We will not really look at acceleration that is a function of time. We will only be dealing with constant acceleration, but in case you have to. Similarly, displacement, the distance covered or displacement is area under velocity time graph, or delta x, which is x1 minus x0, going from some initial time to final time, is velocity time, integral of velocity over time. So this could be possible if you know what is the velocity as a function of time. You can integrate it, and that will give you the displacement of the object. Or if a graph is given to you, just calculate area under the graph, and that will give you displacement. So this could be a possibility, but the first one we usually don't deal with, non-uniform accelerations. I will leave this solved example in there so you can kind of see how area under the curve is calculated. And basically that brings us, maybe let me talk about one example, if I can, on the side fit here, just like FYI sort of thing. So for example, let's say that velocity of an object is negative 4t squared minus 2, as an example. And the time values, the time interval is, initial time is 1 second, and final time is 3 seconds. So total 2 seconds interval. The question is asking what is the displacement of this object during that interval of time. So delta x will be equal to go from 1, which is the initial time, to 3, which is the final time, negative 4t squared minus 2 dt. So we will integrate them one by one. Negative 4 is constant. Integral of t squared is t to the third divided by 3. Limits are 1 to 3. So let's see. And then second part is just negative 2 times t. Again, limits are here. Apply the limits. Negative 4 times 27 over 3 minus, that will become plus 4 over 3 minus 2 times 3 plus 2. Put all of that together, the answer comes out to be negative 38.7 meters. So knowing the velocity function, you can determine that how much distance was covered by the object. That brings us to the end of chapter 2. We talked about a couple of different things, properties of motion, 1D motion. We talked about equations of kinematics, those 4 equations and how to apply them. We talked about graphical analysis, and we looked at free fall motion and how do you get use integration in graphical analysis or with graphical analysis. So basically, how do you get displacement from velocity function, or how do you get velocity from acceleration function? So that is the end of chapter 2.